The potential can be represented on a potential distance graph so that you can see how that potential varies with distance. A graph like this one would show you for a particular planet what the potential would be dependent on that distance from the centre of the Earth. As you can see, it's a curve because V is equal to minus Gm over R. So, if you define potential gradient as the change or the rate of change, the change of potential over change in distance, then what we're looking at is the gradient of a potential distance graph. Now, if you have to work out the potential gradient of a potential distance graph, then what you would do is, on the point in question, you would have to draw a tangent and then work out the gradient of that tangent. Now, why is it interesting and important to work out the potential gradient? Well, by working out the gradient of this graph, what we're doing is dividing a change in potential by a change in R. But of course, this change in potential is equivalent to a change of R here as well. So this should be change in R. What does that give us? The following. As you can see, by dividing the potential by distance, we're actually going back to the field strength. So, the field strength is equal in magnitude to the potential gradient. So, if you work out the gradient of this line, which is equivalent to the potential gradient at this point, you will also be working out the value of the field strength, because potential gradient and field strength are equal in magnitude. What you don't have to worry about anymore is the minus sign, because they're equal in magnitude only. So in this question, consider figure 10.26 and determine the gravitational field strength at a distance 1.5 times 10 to the 7. So if we have a look at that point, 1.5 times 10 to the 7 says 10 to the 7 up here. Okay, so 1.5 would be there, at that point there. So you have to work out a gradient here, which I'm going to try and do now, but it's going to be a nightmare. It should be, oops, hang on. There we go, that's much better. So once you have that tangent, you can work out the gradient, okay, by doing rise over a run. Now, even if you get your tangent just a little bit out of sync, you're going to get a completely different answer to the one given here. But it's worth fiddling about with it and trying getting it as even as possible. Now here we've got a gradient of approximately 5.2 as your rise, so to there, which is 5.2 approximately, and then I've divided it by 3. So this is 5.2 and this is 3. And remember the axes, so in effect it's actually 5.2 that way times 10 to the 8 divided by 3 times 10 to the 7, which gives you about 17.3, 18, could be up to 20 newtons per kilogram. Now, before we go on to anything new, let's review what we've got. Let's look at the relationships between everything. The gravitational force is Gmm over r squared. Gravitational field strength is the force per unit mass. So therefore the gravitational field strength, G, little g, is equal to big G, m over r squared. So what we've done is we've gone from here to here by dividing by m. Now interestingly enough, that's reflected in this side. We know that the gravitational potential energy is equal to minus GMM over R, this time, not R squared. And the gravitational potential, again, is energy over mass. So it's reflecting what's going on here on this side. And we end up with potential, gravitational potential, is minus Gm over R. So what's the difference between these two sides? Well, it's times R. So if you time these, multiply both of these by R, you end up with this. And similarly, if you divide these by M, you end up with these. So it's reflecting. And then between the two, how do we get from here to here? Well, this is a concept of work done. Force times distance. How do we get from here to here? Gravitational field strength times distance. Remember, we talked about the potential gradient, and the potential gradient is gravitational potential divided by distance, gives you field strength, and then similarly, the other way around, it's multiplied by distance. So I'm going to try and put those patterns that you've just seen into the context of some graphs. When we go from this side to this side, what we're doing is we're multiplying by R on both sides, from force to potential energy, field strength to potential. Now, what we're saying there is that the force times distance graph can give us energy. It would be the integral. It would be the area. And in fact, that is a factoid that you can use. The potential energy is equal to the average force times distance, which is equal to the area under a force distance graph. Similarly, field strength times R gives us potential. And that equates to a graph of field strength over R, and the fact that the potential is equal to the average field strength times distance, so therefore it is equal to the area under the field strength graph. So that's going this way. When we go from there to there, or from there to there, we work out the area under the graph, and yes, that means counting squares. Now when we're going the other way, when we're going this way, what we're doing is we are dividing by R, and we can represent this on our graphs as the gradient. So you know that's the case already for a potential gradient. A potential gradient is change in potential over R, and that gives you field strength. So it follows that potential energy divided by R, which is also equivalent to the gradient of a potential energy distance graph, will give you force. So what we are saying, once again, if you go that way, it's area, and if you go this way, it's gradient. Try some questions. Okay, these numerical questions are quite straightforward. The gravitational field strength on the surface of a planet, Venus, is 8.9 newtons per kilogram. Calculate the mass of Venus if it has a diameter of 12,100. So this is just simply using G equals Gm over R squared. But be careful because this is a diameter. Divide this into 2 and don't forget the times 10 to the 3, okay, because it's in kilometers. So really what we're looking at is half this value times 10 to the 3 to plug in for R and square it, okay. The rest of the information we have the gravitational constant, and we also have G, which is 8.9. For part B, we're working out force. So we need to go back to our original formula, F equals GMM over R squared. And once again, we have this in kilometers, so make sure you combine that properly in meters. And just, it's a good point to add, the reason why we must have it in meters is because G, the gravitational constant, is expressed in meters too. So you must make them consistent. So how would we do this question? Well, it's fine. You just substitute in your values using the information from the previous questions. So we have the mass of Venus, which should be 4.9 times 10 to the 24. In there, you have the mass of your object, which is 500, and your distance r squared, and it's just that simple. These questions are pretty straightforward too. There's no need to go over them in too much detail.